Hello there, and welcome to Science for Sleepy Minds. Tonight, we drift together into the vast, silent dark where stars float, like ancient dust across the endless black. Somewhere out there, in a region older than our solar system itself, a small frozen traveler began its journey. Billions of years later, it has finally reached us. Its name is 3I Atlas. It is not just another comet. It is something far more rare, an interstellar visitor, a fragment of another solar system drifting quietly through ours. Only the third such object humanity has ever identified. A quiet messenger, carrying material that formed long before Earth ever existed. A story written across billions of years. Before we begin, if these quiet journeys bring you peace, I invite you to like, subscribe, or leave a thought in the comments. It helps others find their way here too, one sleepy mind at a time. For now, just settle in. Let your breath slow, and let the hush of the cosmic dark carry you far from the noise of the world. Let's begin. Chapter 1. 3I Atlas, a visitor from the stars. On a quiet July evening in 2025, beneath the dark skies of Chile, a telescope was doing what it does every night, watching, scanning the heavens for anything new, anything that moves. The telescope is part of a system called Atlas, a network built to find asteroids that might someday wander too close to Earth. Night after night, it photographs the same patches of sky, looking for tiny points of light that shift against the stillness of the stars. But on July 1st, it found something different. Something unusual. An object moving faster than it should. Following a path that didn't belong to our sun. A path that would carry it through our solar system only once, and then send it back into the darkness between the stars, never to return. Astronomers looked closer. They checked the numbers. They traced its motion backward and forward through time. And slowly, they realized what they were seeing. The third interstellar visitor ever confirmed in human history. A traveler from beyond. For a few weeks after its discovery, the object appeared only as a faint smudge of light. It was near the center of our galaxy, the Milky Way's crowded heart, where tens of thousands of stars cluster together in a glowing haze. That part of the sky is difficult to see clearly. Too much light. Too much dust. Too many stars all pressed together. Small objects can hide there easily, lost among the brightness. In fact, when scientists went back through older photographs, images taken weeks before July, they found it. The comet had been there all along, captured by cameras but unnoticed. Just another dim speck among thousands. Blending in. Waiting. It wasn't until July, when its movement became unmistakable, that it finally stood out. And humanity gave it a name. 3I Atlas. The I stands for interstellar. The third of its kind we've ever seen. The first visitor arrived in 2017. Its name was Oumuamua, a Hawaiian word meaning scout or messenger. It was strange, shaped like a long needle, tumbling end over end. It moved in ways scientists couldn't fully explain. And before they could study it closely, it was gone, slipping back into the deep, leaving only questions behind. The second came in 2019. A comet named 2I Borisov. This one felt more familiar. It had a tail. It glowed softly as the sun warmed it. it behaved the way comets should. It confirmed what many had long suspected, that there are wanderers between the stars. Icy bodies drifting through the dark, occasionally passing through someone else's neighborhood. And now, 3I Atlas, a quiet messenger, carrying with it material that formed long before Earth ever existed, long before the sun ignited, long before anything here had taken shape. 3I Atlas is moving incredibly fast, about 58 kilometers every second, nearly 245,000 kilometers every hour. Imagine that for a moment. Faster than anything bound to our sun could naturally travel. Faster than any planet. Faster than the pull of gravity should allow. That speed is the proof, the signature. It tells us this object doesn't belong here. It came from somewhere else. Perhaps from a distant star's family of planets, a system that once looked like ours, orbiting a sun we'll never see. To make a journey like that takes time beyond imagining. Even from the nearest star, the trip would take millions of years. 3I Atlas may have begun its journey when Earth was still young, when our oceans were just beginning to fill, when nothing had yet crawled onto land. Something, perhaps a giant planet's gravity, or the slow dance of neighboring stars, knocked it loose, sent it drifting. And for billions of years, it moved through the cold and silent dark, untouched by warmth, unnoticed by anyone. Until now. Astronomers estimate that the solid center of 3I Atlas, what they call the nucleus, is about 1 kilometer across. Perhaps as large as 5 kilometers. Hard to say for certain from this distance. But they know it's dense. Heavy. Far heavier than they expected for something its size. Perhaps 33 billion tons of ice and rock, compressed and ancient. That makes it much more massive than Oumuamua. Much heavier than Borisov. And scientists aren't entirely sure why. When sunlight began to reach it, gently warming its frozen surface, something started to happen. The ice inside began to turn to gas. Not melting first, but going directly from solid to vapor, releasing tiny grains of dust along the way. This formed a soft cloud around it. A halo called a coma. Faint and ghostly, stretching thousands of kilometers into space. But here's what's strange. Most comets, when warmed by the sun, grow long, sweeping tails, streams of gas and dust pushed back by the solar wind, glowing bright against the dark. 3I Atlas doesn't do that. Its tail is short, faint, subtle. It's active, yes, releasing gas and dust, but quietly, gently, as if it's holding something back. Some scientists call it a hybrid, part comet, part asteroid, something in between. And it began releasing gas much earlier than expected, when it was still far from the sun, beyond the orbit of Jupiter. Most comets wait until they're closer, until the warmth is stronger. But not this one. It started waking up early, out in the cold, for reasons we're still trying to understand. By October of 2025, 3I Atlas had reached the inner part of our solar system. Around October 2nd and 3rd, it passed near Mars, coming within about 18 million miles of the red planet. That's close enough that spacecraft orbiting Mars could see it. Cameras aboard satellites turned to watch. Even a rover on the Martian surface, a small machine called Perseverance, alone in the dust, looked up and captured a faint glow in the sky. A tiny mark against the stars. Barely visible. But there. On October 29th or 30th, it will reach its closest point to the Sun. Just inside the orbit of Mars. Close enough to feel a little warmth. Close enough for the ice to release more gas, more dust, more of the ancient material it's carried all this way. And then, quietly, it will begin to leave. By early 2026, it will be heading back out into the cold. Back toward the edge of the solar system. Back into the space between stars. At its nearest, it will pass about 270 million kilometers from Earth. That's nearly twice the distance between us and the Sun. Far enough that there's no danger, no risk, only distance, only opportunity. Because it's now positioned near the Sun from our perspective, ground-based telescopes can't see it easily. The glare is too bright, the angle too difficult. But space telescopes can. The James Webb Space Telescope is watching. So is NASA's Swift Observatory. And others. All of them gathering light, measuring brightness, analyzing the faint gases being released. Collecting the story it carries. To the human eye, even through the most powerful telescopes, 3I Atlas appears as nothing more than a small blur. A pale glow. A distant smudge of light. But that tiny point holds something extraordinary. Material from another corner of the galaxy. Ice that likely formed 7 billion years ago, in the cold disk of dust and gas surrounding a young star. Older than our Sun, older than Earth. Older than anything familiar. The particles it releases now, the water vapor, the dust grains, are like messages. Each one carries information. Clues about a place we may never visit. A star we may never see. That's what makes these visitors so precious to science. They are evidence. Physical proof that other solar systems exist, that planets and comets form in places beyond ours, that the building blocks of worlds, and perhaps even life, are scattered throughout the galaxy. Astronomers sometimes call objects like this cosmic messengers. And that's what 3I Atlas is. A traveler carrying quiet information, written in the chemistry of ice and stone. It doesn't speak, but its composition, its brightness, the way it moves, all of these tell a story that instruments can slowly translate into understanding. It's humbling, really, to think that something so small could cross the empty distances between stars, that it could wander for billions of years, untouched, alone, and then, just by chance, pass close enough for us to see. Even now, as it glides through our neighborhood, it remains unchanged, following a path it began long before humans existed. Long before anything on Earth looked up at the sky and wondered. Take a moment, if you will, to imagine it out there. A single visitor. Silent and patient. Ancient beyond measure. Moving steadily past the orbits of the planets. Heading toward the light of the Sun warming, just slightly, after billions of years in the cold. And soon, very soon, it will be gone again, fading back into the dark, continuing its journey to wherever the gravity of the galaxy carries it next. But before it leaves, it gives us something rare, a glimpse, a reminder, that the universe is far larger, far older, and far more mysterious than we can fully grasp. That we are not alone in the sky. That there are other places, other stars, other worlds forming, perhaps, around suns we'll never name. And that sometimes, just sometimes, a piece of that distant universe drifts close enough for us to touch, if only with light, if only with wonder. So let us follow it a little longer. In the moments to come, we'll trace how astronomers first found 3I Atlas, how they confirmed it wasn't one of ours, how they learned to read its faint signals and translate them into knowledge. But for now, just rest. Let your mind drift with it, through the quiet dark. A traveler from the stars, passing through, heading home. Chapter 2: Discovery and Early Observations. When astronomers first noticed the faint light of 3I Atlas, they didn't know what they had found. Not right away. The night sky, especially near the center of our galaxy, is crowded. Thousands upon thousands of stars pressed together. Clouds of glowing gas. Thin veils of cosmic dust. Within all that brightness, a small moving object can easily disappear. The Atlas telescope in Rio Hurtado, Chile, was the first to see it clearly, on July 1, 2025. Atlas is part of a guardian system, a network of telescopes watching over Earth. Its name stands for Asteroid Terrestrial Impact Last Alert System, a long title for a simple purpose: to find anything in space that might be heading our way. Every night, Atlas captures wide pictures of the sky, the same patches, over and over. It's looking for anything new, anything that shifts position even slightly between one photograph and the next. That's how comets and asteroids are found. Not by watching them move in real time, our eyes aren't fast enough for that, but by comparing pictures taken hours apart. If a tiny dot of light appears in one spot, and then another spot a little while later, astronomers take notice. On that July night, a faint point of light did exactly that. It wasn't bright, but it was moving. At first, it looked like a distant comet, soft and blurred, surrounded by a barely visible haze. The Atlas team logged it as a new discovery and gave it a technical name, C2025N1, Atlas. And over the next few days, other observatories around the world began to watch it too. As more telescopes turned their attention to the object, astronomers began to realize something unusual. Its path didn't curve the way a normal comet's would. Instead, it followed what's called a hyperbolic orbit, an open path. A trajectory that would carry it through our solar system only once before sending it back out into the dark, never to return. A hyperbolic orbit is rare. Most comets travel in loops. Long, stretched ellipses that take them around the sun and then back out into the cold outer regions of space. Some loops take years. Some take centuries. Some take millions of years. But they always come back. A hyperbolic orbit doesn't loop. It's an open curve. The object comes in once, swings past the sun, and keeps going. Out into the galaxy. Gone forever. When astronomers calculated 3I Atlas's speed, about 58 kilometers every second, they knew immediately. That was too fast. Far too fast for any comet born in our solar system. Even if a planet had flung it outward with all its gravitational strength, Even if it had been launched from the farthest edges of the sun's influence, it wouldn't be moving this fast. The sun's gravity simply couldn't hold it, and that meant one thing. It came from somewhere else. With that realization, 3I Atlas joined a very short list. Only 2 objects before it had ever been confirmed to come from beyond our sun. The first was Oumuamua, discovered in 2017. Strange, mysterious, shaped like a needle, tumbling through space. It arrived suddenly and left quickly, before scientists could gather much information. The second was 2I Borisov, found in 2019. More familiar. A comet with a tail, glowing softly as it warmed. It behaved the way comets should, confirming what many had suspected, that there are wanderers out there, traveling between the stars. And now, 3I Atlas, the third confirmed visitor. Each one a small but important chapter in the story of how matter moves through the galaxy. How pieces of distant worlds sometimes drift close enough for us to see. To confirm that 3I Atlas truly came from beyond, astronomers looked at something called orbital eccentricity, a number that describes the shape of an orbit. It's simpler than it sounds. For a perfect circle, the number is 0. For an ellipse, an oval, stretched shape, it's somewhere between 0 and 1. But for a hyperbolic path, the kind that never closes, the number is greater than 1. 3I Atlas's eccentricity was well above 1. That confirmed it. The orbit was open. The sun's gravity would tug at it slightly as it passed, slowing it just a little. But once it left the inner solar system, it would keep going, back into the space between stars, never to return. Astronomers from around the world began to coordinate their observations. The Minor Planet Center, the international organization responsible for tracking small bodies in space, officially gave it a new designation, 3I Atlas. The 3I marked it as the third interstellar object humanity had ever identified. Interestingly, after the discovery, scientists went back through older photographs, and they found it. Images taken in mid-June 2025 by both Atlas and another survey called the Zwicky Transient Facility showed the same faint object. It had been there all along. Captured by cameras, stored in files, but unnoticed. No one had recognized it at the time because of where it was. Positioned against the galactic center, one of the most visually crowded regions of the night sky. The galactic center is filled with stars, glowing clouds of gas, ribbons of dust. To pick out one small, moving object against that backdrop takes careful analysis, patience, and sometimes a bit of luck. The discovery on July 1st was a combination of all three. Once the object was confirmed as interstellar, telescopes across the world, and even some orbiting in space, turned their lenses toward it. The excitement in the astronomy community was immediate. One of the most remarkable things about interstellar discoveries is how rare they are. Our solar system is constantly moving through the galaxy. We're surrounded, always, by countless pieces of dust, ice, and rock drifting through space. Yet only a handful of these ever pass close enough to be noticed. That's because interstellar objects are usually very small, very dark, and moving very fast. They don't reflect much sunlight, and their visits are brief, often lasting only a few months before they fade from view, disappearing back into the black. When Oumuamua was discovered in 2017, it stayed bright enough to study for only a short time. Then it was gone. 2I Borisov, found in 2019, was brighter but also fast-moving. So when 3I Atlas appeared in 2025, astronomers knew this was another limited opportunity. A narrow window. A chance to collect as much information as possible before the visitor slipped away. The Atlas team shared the discovery publicly through the International Astronomical Union. Within days, observatories in Hawaii, Spain, and Japan were taking images. Larger facilities, the Keck Observatory, the Subaru telescope on Mauna Kea, joined in soon after, collecting detailed, high-resolution data. The object's brightness changed slightly from night to night. That suggested it was rotating, slowly, perhaps irregularly. Maybe it had an elongated shape, or an uneven surface, one side reflecting more sunlight than the other. But there was something else unusual. Even when it was still far from the sun, more than 450 million kilometers away, well beyond the orbit of Mars, 3I Atlas was already releasing gas and dust. That was unexpected. Normally, comets only become active when they get closer to the sun. Warmth causes the ice on their surface to turn directly into gas, a process called sublimation. But this comet started early. Much earlier than it should have. That suggested its surface was rich in something called volatile materials, substances like carbon dioxide that can vaporize even in weak sunlight, even in the cold. This early activity was an important clue. It hinted that 3I Atlas had formed somewhere cold, somewhere distant, perhaps around a dimmer star, or in the outer edges of another planetary system, where sunlight was faint and ice remained untouched for billions of years. As the days passed, more observatories joined the effort. The Keck Observatory detected faint traces of nickel and cyanide, and signs of complex organic molecules, carbon-based compounds often associated with the early stages of planet formation. NASA's Swift Observatory, observing in ultraviolet light, detected emissions from hydroxyl molecules, a byproduct that forms when water vapor breaks apart under sunlight. This was significant. It was the first time water had been detected from an interstellar object. Later, confirmation came through the James Webb Space Telescope. JWST found that 3I Atlas contained a rich mixture, carbon dioxide, smaller amounts of water vapor, and traces of carbonyl sulfide. The proportions were unusual, different from comets born in our solar system. Each observation added a new piece to the puzzle, and each one raised new questions. In late July and early August, amateur astronomers also began to spot the comet. Using large backyard telescopes under dark skies, mainly in the southern hemisphere, they could see it, a small patch of diffuse light. Faint, but there. For most people, though, 3I Atlas remained invisible. Its brightness never reached the level needed for the naked eye. You couldn't walk outside and point to it. But the sense of wonder spread quickly. Observatories released their first color images online. They showed a soft, slightly greenish glow surrounded by a thin, bluish haze. The pictures looked peaceful, almost understated. A small blur in the darkness, carrying within it an enormous story. Astronomers used every tool available to study it before it became too faint. The Zwicky Transient Facility, Pan-STARRS, Las Cumbres Observatory, all provided measurements of its changing brightness. And each one confirmed something interesting. 3I Atlas was behaving slightly differently than expected. Its glowing cloud, the Comet, brightened earlier than models predicted. Then it stabilized, showing steady but moderate outgassing. By late September, the comet was already too close to the sun's glare for easy ground-based viewing. But space telescopes continued to watch. The James Webb Space Telescope, NASA's Swift Observatory, SphereX, all of them kept recording, capturing infrared and ultraviolet signatures that would later reveal more about the dust and gas the comet was releasing. Each new observation added to the timeline of its journey. Mid-June 2025, first images captured, though not recognized at the time. July 1, 2025, official discovery by Atlas. July through August 2025, a rapid observation campaign begins worldwide. October 1 through 7, 2025, 3I Atlas passes near Mars. Spacecraft orbiting the red planet photograph it. Even the Perseverance rover, alone on the Martian surface, looks up and captures a faint glow in the sky. October 29th or 30th, 2025, the comet reaches perihelion, its closest point to the Sun. Late 2025 into early 2026, it begins its long exit, fading as it moves back into the dark. Each milestone marks a step in its brief encounter with our world. A visit that will never happen again. If you could picture the solar system from above, looking down on it like a map, you would see the planets moving in their familiar circles. Stable, predictable, each one following the same path, year after year. And then, from the far edge of the map, a thin line appears. Fast-moving, cutting across the orbits of the planets in a wide, sweeping curve. It passes near Mars, swings close to the Sun, and then disappears outward again, heading back into the black. That single curve represents millions of years of motion, condensed into a few months of human observation. It's a reminder of how vast space truly is, and how brief our chances are to study the things that pass through it. 3I Atlas gave scientists a rare opportunity, a chance to compare the chemistry of another world to our own, to see how matter travels between stars, to examine the building blocks of distant planets, and perhaps even the ingredients for life, carried across unimaginable distances. Chapter 3: The Journey Through the Solar System. When 3I Atlas entered our solar system, it crossed a quiet threshold that few objects from beyond ever pass. It moved from the cold emptiness between the stars into a space filled with light, warmth, and motion. Unlike most comets that circle the Sun again and again, 3I Atlas is here only once. Its hyperbolic path means that its visit is temporary, a single curve through the plane of our planets before it disappears forever into the dark. Its motion is fast, steady, and unstoppable. Even the Sun, with all its gravity, cannot pull it back. Astronomers have mapped its trajectory carefully. Based on precise measurements, 3I Atlas first entered the inner solar system in July 2025, crossing into the region where the terrestrial planets, Mercury, Venus, Earth, and Mars, orbit. Before that, it had been traveling inward from the outer edge, from beyond Jupiter's orbit, where sunlight is faint and temperatures are near absolute zero. At those distances, it was already active, releasing gas even though the sun's light was still weak. This behavior surprised scientists, who expected such activity only closer in. By the time it reached the inner system, 3I Atlas was already moving at about 58 kilometers per second relative to the Sun, nearly 245,000 kilometers per hour. At that speed, it could travel from Earth to the Moon in just over an hour. Its direction placed it on a descending path through the plane of the solar system. It approached from the southern celestial hemisphere, passed near Mars's orbit, and aimed toward a perihelion distance of about 1.4 astronomical units, slightly inside the orbit of Mars. Around October 2nd to 3rd, 2025, it made its closest approach to Mars, roughly 18.6 million miles, or about 30 million kilometers away. From that distance, it wasn't visible from the Martian surface as a bright object, but sensitive cameras were able to detect it. The ExoMars Trace Gas Orbiter, operated by the European Space Agency, captured a series of detailed images showing a coma, a soft cloud of dust and vapor surrounding the nucleus. The images revealed a faint asymmetry, a slightly brighter region on one side, possibly due to uneven heating as the sun's rays struck it from a particular angle. At the same time, Mars Express, another European spacecraft, recorded similar data. The Mastcam-Z camera on NASA's Perseverance rover managed to capture a very faint patch of light in the sky, a subtle, hazy mark that scientists later confirmed matched the location of 3I Atlas. These observations were historic, the first time a planet other than Earth photographed an interstellar object passing nearby. From Mars, 3I Atlas continued inward, heading toward its closest point to the Sun, its perihelion, expected on October 29th to 30th, 2025. At that moment, it would be roughly 1.4 astronomical units, about 210 million kilometers, from the Sun, well outside Earth's orbit but still close enough to experience significant heating. Astronomers predicted that as it neared this distance, the object's surface would warm to a few hundred degrees Kelvin, enough to drive stronger outgassing and increase its brightness temporarily. However, 3I Atlas didn't behave entirely as expected. Its tail remained faint, even near perihelion. Normally, when a comet approaches the Sun, sunlight and solar wind push dust and gas outward, forming a long, visible tail that can stretch for millions of kilometers. But for 3I Atlas, the tail appeared underdeveloped, short, and diffuse. This suggested that the object might not be shedding large dust particles. Instead, its emissions were dominated by fine grains or gas molecules, which scatter light differently. The overall effect was a bright coma, the glowing cloud near the nucleus, but a faint or nearly invisible tail. To visualize its motion, imagine the solar system as a large, flat disk. The planets move around the Sun in almost circular paths, each orbiting slowly in the same direction. Now imagine 3I Atlas coming in from above that disk at an angle, crossing the planetary plane diagonally, then sweeping down and away again. From our point of view, its trajectory looks like a wide, curved arc. But in reality, it's almost a straight line through three-dimensional space, bending only slightly under the Sun's influence. As it nears the Sun, it accelerates slightly, then begins to slow again once it moves past perihelion. The whole journey through the inner solar system, from entry to exit, takes less than a year. By early 2026, 3I Atlas will already be heading outward, past the orbit of Jupiter, fading quickly as it returns to interstellar space. During its approach, scientists from many countries organized coordinated observation campaigns. The James Webb Space Telescope, JWST, observed it in the infrared spectrum, analyzing how it reflected and emitted heat. These observations helped estimate the composition of its coma and nucleus. JWST confirmed the presence of water vapor, carbon dioxide, and complex organic molecules, but also showed something unusual: low levels of carbon monoxide, CO, a compound that is typically abundant in comets. This chemical difference provided clues about where 3I Atlas might have formed. In regions closer to a star, CO tends to evaporate easily, leaving comets poor in that element. Farther out, in colder zones, CO becomes trapped in ice. The low CO but high CO2 levels in 3I Atlas suggested that it may have formed in a region that was cold enough for CO2 to freeze but warm enough for CO to escape, a delicate balance not commonly seen in our solar system. Each comet carries such signatures of its birthplace, allowing astronomers to piece together the environmental conditions of other solar systems. At the same time, NASA's Swift Observatory observed ultraviolet light from 3I Atlas, confirming hydroxyl OH emissions, a direct indicator of water vapor breaking apart in sunlight. Meanwhile, SphereX, a mission designed to study how light scatters off cosmic dust, measured the polarization of the comet's light. The results showed unusual polarization patterns, meaning the dust particles in 3I Atlas might have irregular shapes or unique compositions not seen in solar system comets. This combination of data, from JWST, SWIFT, SphereX, Keck, and other ground-based observatories, provided a complete picture of the object as it traveled. Every wavelength of light told a slightly different story. In October 2025, just before perihelion, the Solar and Heliospheric Observatory, SOHO, attempted to detect it using its wide-field cameras. There was hope that the comet might become visible as a faint streak near the Sun, but glare and distance made it difficult to confirm. Still, the data collected across these missions ensured that even as the comet faded from view, its characteristics would be preserved in archives for decades of study. And the observations didn't stop there. In November 2025, the Jupiter Icy Moons Explorer, JUICE, a European spacecraft en route to study Jupiter's moons, was scheduled to turn its instruments toward 3I Atlas. From its vantage point in the outer solar system, JUICE could look at the comet from behind, capturing how sunlight scattered through its halo and tail. Even faint measurements could add valuable insight into the size of the dust particles and how they were released. To the human eye, all of this happens invisibly, quietly. Yet, if we could somehow watch in real time, we would see a breathtaking sight. A small, glowing point of light, moving steadily against a backdrop of stars. Near Mars, it glows softly, with a pale greenish tint from the gases in its coma. As it nears the Sun, it brightens briefly, then dims again as it turns outward. The coma expands and fades, its gas dissipating into space, merging with the solar wind. And then, slowly, it drifts away, smaller, fainter, quieter, until even the largest telescopes can no longer find it. But it doesn't stop moving. It will continue beyond the outer planets, beyond the Oort cloud, and back into interstellar space, carrying its record of chemistry, structure, and motion through the galaxy. The total distance it travels through our solar system, from the moment it entered to the moment it leaves, is measured in billions of kilometers. Yet, Compared to its overall journey through the Milky Way, this passage is just a short detour, a single step in a voyage lasting billions of years. At its current speed, 3I Atlas will eventually travel hundreds of trillions of kilometers away from the Sun. It may pass near other stars millions of years from now, just as it passes ours today. Perhaps in another distant system, it will be detected again, faint but visible, a reminder that the galaxy is full of such wanderers, fragments of ancient systems quietly moving through the void. By observing 3I Atlas, scientists not only learn about one comet, but also gain perspective on the connections between star systems. It shows that material doesn't stay confined to where it formed. Ice, rock, and dust can be exchanged between stars, blending the elements of one world with another. In a sense, 3I Atlas carries a sample of another star's history, drifting through space until chance brings it to us. For all our advanced technology, the discovery of such objects still depends on timing, patience, and a bit of luck, the right telescope looking in the right direction at the right moment. Its visit is brief, but its significance will last for decades. The data gathered from this journey will help scientists refine models of comet behavior, understand interstellar chemistry, and perhaps estimate how common these travelers really are. Already, astronomers are preparing for the next time such an object appears. Each one teaches us a little more about the universe, about what exists between stars, and how those materials may have helped seed life and planets in systems like our own. Now, as 3I Atlas approaches the end of its journey through our solar system, it slows slightly. The sun's pull weakens. The coma fades. The gases cool and condense, and the nucleus returns to silence. By early 2026, it will have passed the orbit of Jupiter, becoming too faint for any telescope to see. After that, it will drift back into the interstellar dark, carrying with it the quiet record of this brief encounter, a record that now lives in our instruments, our data, and our understanding. It came, it shone faintly for a while, and then it left, unchanged, unbroken, still on its long path through the galaxy. Chapter 4. The Shape and Nature of its Core. When astronomers observe a comet, they are usually looking at a soft cloud of gas and dust, not the solid body beneath it. The nucleus, the true heart of a comet, is small and faint, hidden within the glow of its coma. For 3I Atlas, that core is the part scientists have studied most carefully, because it holds the real story of where this visitor came from and what it has endured across billions of years. The first step in understanding it is to measure its size and shape. For a distant interstellar comet like 3I Atlas, that is not simple. It appears as only a small blur, even through powerful telescopes. To estimate its true form, scientists rely on how bright it looks, how that brightness changes over time, and how light scatters through the surrounding dust. The results suggest that 3I Atlas has a nucleus about 1 kilometer wide, roughly 0.6 miles across. Some models, however, allow for a slightly larger body, perhaps up to 5 kilometers. This range is still small by cosmic standards, but significant for an interstellar object. If it is toward the larger end, its total mass could reach tens of billions of tons, around 33 billion tons by some estimates. That makes it one of the most massive interstellar visitors ever recorded. The nucleus itself seems irregular or elongated rather than round. Another observation came from the James Webb Space Telescope, which measured the thermal emission from the coma. The temperature and reflectivity data suggested that the nucleus surface might be covered by dark, carbon-rich material that absorbs sunlight efficiently. Such material, often called tholins, forms when radiation alters organic compounds on icy surfaces. These substances are found on the outer moons of our solar system, such as Pluto and Triton, and give them their reddish-brown color. If 3I Atlas has a similar coating, it may have spent much of its history exposed to cosmic rays in interstellar space, slowly darkening over time. This would also help explain why it began outgassing so early. Dark material absorbs more heat, causing localized warming even at great distances from the Sun. Based on modeling of its motion, the nucleus of 3I Atlas probably rotates slowly, completing a spin in several hours. A slow rotation helps maintain a stable coma and reduces the risk of fragmentation, something that can happen when fast-rotating comets experience uneven heating. So far, there is no evidence that 3I Atlas is breaking apart. It appears to be holding together well, despite its journey toward perihelion. This stability contrasts with some other comets, which sometimes split or crumble when approaching the Sun. Its durability may be another clue to its composition. A rockier or denser structure could resist thermal stress better than a loose, fluffy body. All of these clues, the mass, the early activity, the unusual polarization, and the faint tail, build a picture of a comet that is both familiar and foreign. It behaves partly like comets we know, yet differs in ways that challenge our assumptions. In a way, it seems to sit between the two earlier interstellar visitors. Oumuamua was dry, solid, and lacked a visible coma. 2I Borisov was highly active, resembling a typical comet with a long, bright tail. 3I Atlas is somewhere in between, active but subtle, icy but massive, and uniquely complex. Its nature suggests that the diversity of interstellar objects may be greater than we once thought. There may be countless variations, each representing a different kind of birthplace and history. From a scientific perspective, the nucleus of 3I Atlas is a time capsule. Its material may date back 7 billion years, older than our solar system. In that time, it has likely remained frozen, untouched, and unchanged until this moment of passage through our Sun's light. By studying it, astronomers can glimpse the chemistry and structure of a planetary system that no longer exists, or one that evolved very differently from our own. Each gas molecule released now, every puff of vapor and grain of dust, carries information about its composition. Instruments detect these signals, analyze their spectra, and translate them into data about temperature, composition, and molecular bonds. This is how we learn about something so small and so far away. Through light, through motion, through the quiet traces it leaves behind. Chapter 5: The Coma and Tail. Every comet that travels near the Sun begins to change. Frozen materials locked in darkness for billions of years start to warm. The heat of sunlight slowly penetrates the outer layers, and the surface begins to release gas and dust. These escaping particles form a thin, glowing cloud that surrounds the nucleus, what astronomers call the coma. For 3I Atlas, the coma is one of its most studied features. It is the visible sign of activity, the first thing telescopes detect when they point toward the object. And yet, its appearance is unusual, brighter and larger than expected, but with a faint and short tail. To understand why, we can look closely at how it behaves as it travels near the Sun. When sunlight hits the surface of 3I Atlas, energy begins to break the bonds that hold its frozen materials together. The gases trapped within, mainly water vapor, carbon dioxide, and trace elements, escape into space, carrying along fine particles of dust. These particles scatter sunlight, creating the diffuse glow of the coma. Even a small amount of released gas can make the coma expand to enormous sizes, sometimes thousands or tens of thousands of kilometers wide. For 3I Atlas, the coma was measured to be several thousand kilometers across as early as July 2025, when it was still far from the Sun. The gases were already streaming outward at high speeds, forming a faint, expanding halo. This was unusual because most comets only develop a visible coma when they are much closer to the Sun, around 3 astronomical units or less. 3I Atlas began outgassing, meaning it was active even in the cold outer regions beyond Jupiter's orbit. That early activity told astronomers something important: its volatile materials were different. Instead of being driven primarily by water ice, which needs stronger sunlight to vaporize, its activity was likely caused by carbon dioxide, CO2, and possibly carbonyl sulfide, both of which sublimate at lower temperatures. This discovery explained why the coma appeared earlier and brighter than expected, but also why the tail was faint. The tail of a comet forms when solar radiation and the solar wind, a stream of charged particles from the Sun, push dust and gas away from the nucleus. The lighter the particles, the easier they are blown outward, forming long, graceful streaks that point away from the Sun. But 3I Atlas's tail was weak and short, barely extending beyond its coma. The dust particles it released might have been too small or too heavy to be pushed far by the solar wind. Another possibility is that it was releasing mostly gas, not dust, which would create a diffuse, nearly invisible tail detectable only in specialized wavelengths of light. Images taken by telescopes such as Keck, JWST, and Mars Express confirmed this. They showed a bright central coma with a gradual fade, but no long visible streak. To the human eye, if we could see it through a large telescope, it would appear as a round patch of light with a slight elongation on one side, subtle and soft, without the dramatic tails seen in more familiar comets like Hale-Bopp or Neowise. The coma's color and texture also offered clues. Spectroscopic studies found that it emitted light in the green and blue regions of the spectrum, caused by small amounts of cyanide, Cn, and diatomic carbon, C2. These compounds are common in comets and often produce the faint greenish hue seen in their comae. However, in 3I Atlas, the green emission was weaker than normal. Instead, much of its light came from reflected sunlight off dust grains. This indicated that the gas production was relatively low compared to the amount of dust, an uncommon trait for such an active comet. Further analysis by SphereX and Keck showed that the dust grains were fine and irregularly shaped, producing an unusual polarization signal. This finding linked back to earlier evidence that the dust itself was not like that found in typical comets of our solar system. These grains could be porous aggregates, loosely clumped structures that scatter light in complex ways. Their behavior might explain why the tail didn't extend far. Instead of being blown away cleanly, the dust may have spread out in all directions, creating a large but diffuse cloud rather than a narrow, visible streak. As 3I Atlas moved closer to the Sun in October 2025, its coma brightened slightly. Observations from the James Webb Space Telescope showed subtle increases in infrared emission, indicating more heat and gas release. But even near perihelion, the point of closest approach to the Sun, the coma remained well-defined and stable. It did not flare dramatically or fragment, something many comets experience under thermal stress. This stability suggested that the nucleus surface was not highly porous or fragile. Instead, it may have a crust or hardened outer layer that limits gas escape. Through small cracks or vents, gases could still escape steadily, maintaining a moderate but consistent coma without large eruptions. This kind of behavior makes 3I Atlas a valuable case study for understanding how comets evolve when they travel between star systems. A hardened crust could form during millions of years in interstellar space, where cosmic rays and micrometeoroid impacts gradually alter the surface. Over time, the outermost layers may lose their more volatile components, becoming compact and stable, a kind of natural shielding. When such an object enters a new solar system, only the materials just below that surface layer become active. Some astronomers compared its coma to that of Comet 67P Churyumov-Gerasimenko, the comet visited by the European Space Agency's Rosetta mission in 2014. That comet, too, had regions of differing activity, some quiet, others venting strongly. If we could see 3I Atlas up close, its surface might show similar patterns. Areas of bright gas release surrounded by darker, inactive planes. But for now, those details remain hidden. Instead, we read its behavior through light curves and spectra, letting the data tell the story silently. The coma's structure changed gradually as 3I Atlas approached and passed perihelion. Before October 2025, it showed a tight, symmetric shape, smooth and even. Near perihelion, solar heating may have caused slight asymmetries, as one side of the nucleus faced the Sun more directly. After perihelion, as it began to move away, the coma slowly expanded and dimmed, fading back into the darkness. Each change was subtle, observed through the patient accumulation of thousands of images. The process reflected a kind of calm consistency, a small object reacting to the warmth of the Sun in measured, predictable ways. The tail, though faint, revealed its own information through specialized instruments. Ultraviolet observations from NASA's Swift Observatory detected faint lines of hydroxyl emission, evidence of water molecules being split by sunlight. These emissions extended outward from the coma in the expected direction, confirming that the comet did, in fact, have a tail, just one too faint for visible light observation. Infrared instruments measured how the gases spread and cooled. By mapping this data, scientists could estimate the rate of gas production. 3I Atlas was releasing roughly a few kilograms of water vapor per second near perihelion, modest compared to typical solar system comets, which can release hundreds of kilograms per second at similar distances. This low activity level matched its subdued appearance and explained why its coma remained bright and stable rather than chaotic and flaring. The study of the coma and tail is more than just a visual exercise. It helps scientists understand how interstellar objects preserve and release materials. Each component of the coma, dust, ice, and gas, carries a chemical record. By comparing those components to comets in our solar system, researchers can see whether the same basic chemistry occurs elsewhere in the galaxy. In the case of 3I Atlas, the mixture of water, carbon dioxide, trace organics, and nickel-bearing dust suggests a formation environment rich in metals and carbon, perhaps a disk surrounding an older star. If true, this would make it a piece of an ancient planetary nursery, preserved for billions of years before drifting across interstellar space and entering our solar system by chance. Its faint tail also carries implications for how comets might behave when moving between stars. In deep space, without solar radiation, a comet remains inert, its gases locked within. Over time, the more volatile materials escape slowly through tiny fractures, leaving behind a tougher, more stable core. By the time it encounters another star, only certain compounds remain to react to heat. 3I Atlas's faint tail and early, CO2-driven activity fit this pattern perfectly. It is the picture of an old traveler, not lifeless, but quiet, releasing what little remains of its volatile energy as it passes through our system. This insight helps astronomers estimate what percentage of interstellar objects might still be active when we detect them. Many may pass by completely unnoticed, dark and silent, never close enough to show a visible coma at all. In this way, 3I Atlas becomes not just an object of study, but a representative of an entire unseen population. Billions of icy relics moving through the galaxy, each carrying traces of its origin. Its coma and tail, though modest, give us real evidence of interstellar chemistry, the direct observation of water and carbon compounds from beyond our solar system. It shows that such materials exist not just here, but throughout the Milky Way, linking worlds together through shared elements and ancient dust. As it moves farther from the Sun, the coma fades slowly, the gases cool, and the tail disappears. The nucleus remains, dark and quiet again, ready to continue its long journey. If we could follow it beyond Jupiter, we would see the glow shrink to nothing. Just a small, inert body slipping back into shadow. It will travel for millions of years before sunlight from another star warms it again. Its faint tail, once a trace of light and gas, will have dispersed completely into the solar wind, joining the particles that drift endlessly through interplanetary space. Chapter 6: The Chemistry of an Ancient Object. When astronomers study comets, they are really studying chemistry, the frozen chemistry of the early universe, preserved in small, icy archives. Every gas and grain of dust that escapes a comet's surface tells a story about its origin, the environment where it formed, and the conditions it has survived since then. 3I Atlas, being an interstellar visitor, offers a special kind of story. It comes not from our sun's disk of planets and dust, but from a completely different system, perhaps one that no longer exists. Its chemical makeup is a message from another star, sent billions of years ago, and received only now. By examining its gases, its dust, and the faint light they produce, scientists can compare its chemistry to the materials found in our own solar system. The differences and similarities between them reveal how universal, or how varied, the building blocks of planets might be. The composition of 3I Atlas is unlike that of any comet observed before. Early observations by JWST, Keck, and Swift detected strong emissions from carbon dioxide, CO2, and water vapor, with smaller amounts of carbon monoxide, CO, and carbonyl sulfide, OCS. This is an unusual combination. In most comets within our solar system, carbon monoxide is one of the most abundant gases released when the nucleus warms. It is a highly volatile compound that vaporizes even at low temperatures. Carbon dioxide is also common, but typically in lower concentrations compared to CO. 3I Atlas showed the opposite pattern, high CO2 and low CO. This inversion provides an important clue. It suggests that the comet formed in an environment where temperatures were just warm enough to drive away much of the CO gas, but still cold enough for CO2 to freeze. Such conditions might occur near the outer edge of a young planetary system, beyond the so-called snow line, where ices can condense but radiation from the central star remains strong enough to shape their chemistry. If that system's star was dimmer or older than our Sun, its temperature gradients would have been different, leading to a different balance of frozen materials. Alongside CO2 and water, 3I Atlas contains small amounts of cyanide, Cn, hydroxyl, OH, and traces of nickel, the latter detected by Keck's spectrograph. Cyanide molecules, often seen in comets, are indicators of organic chemistry. They form easily in cold interstellar clouds and are considered key building blocks for more complex organic compounds. Hydroxyl, on the other hand, is a direct product of water vapor being broken down by sunlight, a reliable marker of water-ice sublimation. The detection of hydroxyl was particularly exciting because it marked the first confirmed observation of water from an interstellar object. Both previous visitors, Oumuamua and Borisov, hinted at ices but lacked direct confirmation. Here, with 3I Atlas, the presence of water is beyond doubt. This means that at least some interstellar comets, objects formed around other stars, carry water ice just like ours do. The same molecule that shapes our oceans and clouds appears to be common even in the distant regions between stars. The discovery of water vapor from 3I Atlas carries profound implications. It means that water formation is not unique to our solar system. Wherever dust and gas gather around young stars, the same chemistry may take place, hydrogen and oxygen combining on the surfaces of cold grains to form ice. Over millions of years, those ices become part of larger bodies, comets, asteroids, or even planets. When one of those bodies is eventually thrown out of its home system, it drifts through interstellar space, carrying its frozen record. 3I Atlas is such a traveler, still holding the molecules that condensed around another star billions of years ago. That makes every detection of water, carbon dioxide, and organics in this object a kind of verification. A proof that the processes that created Earth's water likely happen everywhere. Astronomers also noticed that 3I Atlas emits more gas than expected at long distances from the Sun. Normally, comets become active at around 3 astronomical units, when sunlight is strong enough to sublimate water ice. But 3I Atlas began releasing gas. This early activity indicates that carbon dioxide, not water, was the main driver. Carbon dioxide sublimates at lower temperatures than water ice, meaning it can vaporize with only gentle heating. At those distances, the solar energy reaching 3I Atlas is only a small fraction of what Earth receives. Yet, it was enough to awaken the gases beneath its surface, suggesting that they were abundant and close to the outer layers. This early outgassing behavior makes 3I Atlas unique among known comets. It may even redefine how scientists look for future interstellar objects, since their activity could begin much farther out than previously expected. Data from the James Webb Space Telescope provided a detailed look at the proportions of gases in the coma. JWST's infrared spectrometer detected a strong CO2 absorption band, confirming that carbon dioxide was the dominant volatile component. Smaller but significant features showed water vapor, carbonyl sulfide, OCS, and formaldehyde-like compounds, simple organic molecules that can form more complex substances under the right conditions. The mix of these compounds points toward a rich chemical environment, one that included carbon, oxygen, and sulfur in stable, reactive forms. These are the basic ingredients for prebiotic chemistry, the kind that can eventually lead to amino acids and other molecules related to life. 3I Atlas, therefore, carries not just water, but the same family of chemicals that may have seeded the early Earth. Interestingly, its dust composition also hints at complexity. The Keck telescope's polarimetric data showed that the light scattering off the Comet's dust was negatively polarized, meaning the particles interacted with light in a reversed pattern compared to typical solar system comets. This indicates that the dust grains are either highly irregular, very porous, or coated with dark, complex organics. Such dust would absorb sunlight efficiently, helping to warm the surface slightly even in weak light. This could explain the early onset of activity and the steady, gentle outgassing rather than explosive flares. It also suggests that 3I Atlas's dust has been processed by cosmic rays over billions of years in interstellar space. Radiation alters ices and organics, creating new compounds, sometimes reddish, sometimes black, often chemically stable. These processed materials are found elsewhere, too, on outer solar system bodies like Pluto, Eris, and Triton, showing that cosmic radiation sculpts matter in similar ways across the galaxy. Another insight came from infrared thermal studies. The temperature of the coma, measured by JWST and confirmed by smaller observatories, remained relatively low, around 150 Kelvin, or about -120 degrees Celsius. This indicates that much of the energy from sunlight went into sublimating ices rather than heating the surface. In simple terms, the comet was spending its energy releasing gas, not warming up. That efficient cooling effect helped it stay stable and prevented violent breakups that sometimes occur in comets with more brittle structures. Chapter 7: Eyes on the Sky. Telescopes and Missions. When something as rare as an interstellar visitor enters our solar system, the first reaction from the scientific world is curiosity, and then coordination. No single telescope can capture every aspect of a fast-moving, distant object like 3I Atlas. It takes many instruments, spread across Earth and space, to watch it, measure it, and understand what it reveals. From the moment 3I Atlas was discovered on July 1, 2025, an international network of observatories began to observe it, working together quietly, across continents and orbits, to collect as much data as possible before it faded again into the dark. This chapter follows those eyes, the instruments that turned toward the visitor, each providing a different perspective on its brief, luminous passage. The first watchers, the Atlas Telescope Network. The story began with the Asteroid Terrestrial Impact Last Alert System, or ATLAS. This network, operated by the University of Hawaii and supported by NASA, consists of multiple small telescopes located at different sites, including Rio Hurtado, Chile, where 3I Atlas was found. ATLAS is designed for safety. It scans the skies nightly for objects that might come close to Earth, acting as an early warning system. But in doing so, it also finds things that pose no threat at all. Objects like comets, asteroids, and sometimes, as in this case, visitors from beyond. When 3I Atlas first appeared on Atlas's wide-field camera images, it was just a faint moving. The system automatically flagged it as a possible new object. Over the next few nights, follow-up images confirmed that it was not an asteroid on a circular path, but something faster, something whose orbit didn't curve back around the Sun. The discovery was announced through the Minor Planet Center, and the object received its official name, C2025N1 Atlas, later reclassified as 3I Atlas, marking it as the third interstellar object in history. Ground-based observatories, Keck, Subaru, and the World Network. Once its interstellar nature was confirmed, some of the world's most powerful ground telescopes began to follow it. The Keck Observatory in Hawaii, with its 10-meter mirror, observed 3I Atlas using high-resolution spectroscopy. This allowed scientists to identify faint chemical signatures, carbon dioxide, nickel, cyanide, and organics, in the light from its coma. Keck also detected the object's polarization pattern, revealing that its dust grains had unusual reflective properties. Nearby, the Subaru telescope, also on Mauna Kea, captured deep images that helped refine its trajectory and brightness over time. Subaru's wide-field camera was particularly useful for monitoring how the coma evolved and whether the comet's structure changed as it approached the Sun. Meanwhile, the Very Large Telescope, VLT, in Chile contributed infrared data, measuring how heat radiated from the nucleus and coma. The VLT's adaptive optics provided some of the sharpest images available from Earth, showing a well-defined coma but no obvious tail. Smaller observatories around the world joined in. Pan-STARRS in Hawaii, which specializes in scanning wide areas of sky. Zwicky Transient Facility, ZTF, in California, which helped find earlier pre-discovery images from mid-June 2025. Las Cumbres Observatory Network with robotic telescopes in both hemispheres, providing continuous monitoring. Together, they formed a web of observation that followed the comet from its discovery through late summer 2025. Space-based observatories, seeing beyond Earth. Ground-based telescopes can do a great deal, but they have limits. The atmosphere distorts light, and sunlight can obscure faint objects near the Sun. So, astronomers also relied on telescopes in space, above the Earth's atmosphere, where clarity is absolute. The James Webb Space Telescope, JWST, played a central role. Using its powerful infrared instruments, JWST was able to analyze the composition of the comet's coma in unprecedented detail. Its data confirmed high levels of carbon dioxide, significant water vapor, and traces of organic molecules. It also measured the temperature and reflectivity of the dust, showing that the particles were fine and coated in dark, radiation-processed material. JWST's sensitivity allowed it to detect these signals even when the comet was faint and distant, providing the first precise chemical fingerprint of an interstellar comet. At the same time, NASA's Swift Observatory, which observes in ultraviolet and X-ray wavelengths, detected hydroxyl emissions, a clear indicator that water molecules were breaking apart under sunlight. This confirmed the presence of water ice in 3I Atlas, a discovery of profound importance, as it proved that water-rich bodies exist even outside our solar system. Another instrument, SphereX, designed to map the sky in infrared light, studied how light scattered through the coma and measured the polarization of the reflected sunlight. The results revealed the unique texture of the dust, supporting the idea that it might be unlike anything found locally. Planetary missions. Watching from Mars. As 3I Atlas moved inward, it passed closest to Mars around October 2nd to 3rd, 2025, at a distance of about 18.6 million miles. This was a special opportunity. For the first time, a planet other than Earth could observe an interstellar visitor up close. The European Space Agency's ExoMars Trace Gas Orbiter, TGO, was among the first to capture it, photographing a small, glowing cloud against the backdrop of stars. The Mars Express spacecraft, also operated by ESA, followed with its own set of images and spectra, confirming the same faint but consistent glow. Meanwhile, on the Martian surface, NASA's Perseverance rover turned its Mastcam-Z camera toward the sky and caught a subtle, elongated mark, a light smudge barely visible against the horizon. Later analysis confirmed it was indeed 3I Atlas. These images represented a quiet milestone in astronomy. The first observations of an interstellar object made from another planet. For planetary scientists, it was a humbling reminder that even across vast distances, exploration is now multi-world, Earth and Mars observing the same traveler at the same time. Solar observatories, watching near the Sun. As 3I Atlas approached perihelion in late October 2025, it grew too close to the Sun for most ground telescopes to see. Instead, attention shifted to solar observatories. The Solar and Heliospheric Observatory, SOHO, a joint ESA-NASA mission, scanned the region around the Sun using its wide-field coronagraphs. Scientists hoped that SOHO might catch a glimpse of 3I Atlas as it brightened briefly during its closest approach. While the object's faintness and angle made it difficult to detect directly, the data collected helped model how its coma interacted with the solar wind. In a way, its fading is a return to what it has always been, a silent traveler, unnoticed, carrying its ancient materials through endless space. What it means for science. For astronomers, the study of 3I Atlas is only beginning. The data collected during its passage will take years to analyze fully. Each spectrum, each image, each light curve contains layers of information about temperature, composition, and structure. From this data, scientists will refine models of planetary formation, test theories about interstellar chemistry, and improve methods for detecting future interstellar visitors. Already, new telescope surveys are being planned, instruments that will look deeper and wider, watching for the next faint object moving too fast to belong to our Sun. When that next visitor arrives, we'll be ready, better equipped to catch it early, follow it closely, and learn even more. In this way, 3I Atlas has already shaped the future of astronomy. What it means for science. For astronomers, the study of 3I Atlas is only beginning. The data collected during its passage will take years to analyze fully. Each spectrum, each image, each light curve contains layers of information about temperature, composition, and structure. From this data, scientists will refine models of planetary formation, test theories about interstellar chemistry, and improve methods for detecting future interstellar visitors. Already, new telescope surveys are being planned, instruments that will look deeper and wider, watching for the next faint object moving too fast to belong to our Sun. When that next visitor arrives, we'll be ready, better equipped to catch it early, follow it closely, and learn even more. In this way, 3I Atlas has already shaped the future of astronomy. The broader meaning. Beyond the science, the story of 3I Atlas reminds us of scale and connection. We often think of our solar system as a small, self-contained world, but it is part of something larger, a galaxy of motion, where even distant stars share their dust and ice. When we observe an interstellar comet, we are not looking outward as much as looking across a network of systems that exchange matter, light, and history. In the quiet of that realization, there's a sense of belonging. The same carbon that burns in the Sun's light exists in 3I Atlas. The same water that flows in our oceans sublimates from its surface. The same nickel that shapes our planet's core lies buried in its dust. It is not foreign. It is familiar. It is part of the same process that formed us. A moment in time. Our observation of 3I Atlas is a fleeting moment in a timeline that spans billions of years. For us, it is new, a discovery, an event, a chapter in scientific history. For the comet, it is one brief passage through light before returning to the dark it has always known. By 2026, it will be gone from our view. By 2030, its distance will be so great that no instrument will detect it. And yet, it will still be moving, unchanged, carrying the chemistry of another world through interstellar space. Somewhere, millions of years from now, it might pass near another star. Perhaps another civilization, looking out from their own world, will notice a faint moving light in their sky, and wonder where it came from. If they study it closely, they might find traces of our sun's warmth on its surface, a chemical echo of its brief time here. In that sense, 3I Atlas will continue to share information long after we've lost sight of it. A quiet legacy. Its legacy is simple and profound. It showed us that the space between stars is not empty. It proved that the materials of life and planets exist everywhere. It reminded us that discovery is still happening, even in an age when we often think we've already seen everything. It also demonstrated what humanity can do when it looks together. Hundreds of observatories, scientists, and enthusiasts around the world worked in harmony to observe a visitor that none of us will ever see again. That unity of attention, that quiet collaboration, is its own kind of beauty. The data we have gathered will continue to teach for decades. But perhaps the greater lesson is not just in the numbers, but in the perspective, that the universe is vast, alive with motion, and still full of things we have yet to understand. The return to stillness. If this quiet journey brought you peace, I invite you to like, subscribe, or leave a thought below. It helps others discover these gentle explorations, one sleepy mind at a time. For now, simply rest. Let your thoughts travel with that distant wanderer as it returns to the space between stars. Somewhere